Question. I'm sorry. Uh, people often wonder about this. So I'm gonna write down something general. I don't know what it says in here. I want to do it a couple way. One of them sort of like a album way, and then we'll do it maybe a little bit more rigorously by induction, but it's not perfect. You all have seen this, right? Right, that's an oldie but a goodie, right? And right, so if you really want to show off to your friends too, I know a cubic too, right? But how do we get this, right? I mean, these numbers seem kind of random, maybe they talk about Pascal triangle. So I'll do the specific example before I give the first proof of binomial theorem. That's really what you're doing. So the way you get this probably back in high school is you multiply this out to this, and then you put another factor in there and multiply that again, right? Well, let's see if we can do this a shorter way. What are you doing? You're adding up a bunch of stuff that has X's and Y's in it, right? And basically what you're doing is you're choosing a representative from each one of these parentheses, right? Notice that you might have an X out of here, an X out of here, and a Y out of here. You might have a Y here, an X here, and a Y here. And that's basically the product you're forming. Everybody okay with that? That's Y, by the way. Notice there's an X cubed, X squared Y, X Y squared, and Y cubed. Notice the powers of X and Y put together always come to 3, right? Well, so let's make some choices. I can do X cubed, and there's only one way to do it. I gotta pick the X, the X, the X. Everybody agree with that? By the same token, I can get a Y cubed, and I have to do it by picking the Y, the Y, and the Y, right? What are my other possibilities? Well, I can pick 2 X's and a Y. And how many ways are there to do that, pray tell? X, X, Y, X, Y, X, Y, X, X. 3 ways to pick 2 X's and a Y. That's that. I can also pick 1 X and 2 Y's, right? How many ways are there to do that? Also 3. Your X either comes here, here, or here. Let's do just one more. I mean, if you want to up the voltage. And I think this one more example might help us move to higher ground. What if we did to the 4th power? Well, there's only one way to get, all your powers are going to be forced because you're picking 1 out of each of these, right? So even if it's X squared, Y squared, that's still could count that as 4th power. There's only one way to pick all X's and only one way to pick all Y's. What else could I do? I could do 3 X's and a Y. How many ways are there to do that? Well, I've got to get 3 X's and only 1 Y, right? So ask yourself this: how many places can I pick the Y from? 1, 2, 3, 4. Must be 4 of those. You know what? I bet this is mirror symmetry here. Four ways to do that as well. How many ways are there to pick 2 X's and 2 Y's? Ask yourself this. Once I pick my 2 X's, I know where my 2 Y's are coming from. Everybody agree with that? 2 X's, 2 X's, 2 X's, 2 X's, 2 X's, 2 X's. How many was that? 6. 6, right. Well, okay, so okay, let's get real bold. Well, so this is going to be uh, so now, let's think of this. Let's think of this product of entities. How many ways are there to get all X's except for 1? Well, right, there's a, right? Because ask yourself this, how many ways can I pick my Y? It can either come from here, or here, or here, so forth, so on. There's N. Right? How about this? This is where it gets a little bit trickier. But this is important, I think, to see patterns. Now, this is a little bit more complicated, right? Because now you're not just picking 1 Y. That was easy to get out of here. Now you're picking 2, right? How many ways are there to do that? Well, you go systematically through this. Pick your 2 Y's from here, or here, all the way down, right? That's all the ways you can do it. Pick them first Y from here, or here down, or here down. Just, it sounds like a long list, right? What should this number signify? I'm trying to find my 2 places I'm picking my Y from. Everybody agree with that? So I am asking myself, how many subsets of order 2, that's where I'm picking my Y from, are there from the set of order N? Because there's N products. Remember what this was. This is the number of ways to pick 2 sets out of a subset of order 2 out of a set of order N, right? What do you suppose the pattern is going to be here? Now I've got to pick Y thrice, right? So I'm looking at the number of subsets of order 3 from set of order N. Everybody okay with that? This is really less of a proof, but more where the formula comes from. You continue this on down, and it's symmetric. N choose 3, X cubed, Y N minus 3, plus N choose 2, X squared, Y N minus 2, plus N choose 1, X Y N, plus Y N minus 1, Y N. And that's why the binomial coefficient is what it is, because when you try to determine what is the coefficient of x to the k, y to the n minus k, how many ways are there to do this? You've got to pick x exactly k times, right? And y the remaining times, right? So ask yourself this: self how do I pick X out of this K times? You're asking yourself, how many subsets of order K are there in a set of n things in the product? Everybody agree with that? And, Nick, I think it was you that asked earlier, why is n choose K equal to n choose n minus K earlier in class today? This shows you why, right? Because picking K of these is the same thing as picking n minus K of the other. And that's another way. We actually proved this with this symmetry here. Now, good practice on induction. Let's actually prove this more solidly via induction. And let me remind you. Notes. Let me put up something that we might want to use.
Oh, really?
Actually, I think this is the last thing that I proved in class last time. Right? I put this up here because I think we're going to need this. Let's prove this by induction. You've got to love the base case of this one, right? It's going to be easy, I bet. Equals 1. That's right. Sure. Well, actually, let me start this way. It'll be more elegant. If I look at the sum, n equals k equals 0 to 1. 1 choose k, x to the 1 minus k, y to the k. Let's see what this is, shall we? First, plug in k equals 0. I get 1 choose 0, x to the 1, y to the 0. Right? Second term, that is when k is 1. 1 choose 1, x to the 0, y to the 1. Right? 1 choose 0 and 1 choose 1 are both 1. The base case in a very boring calculus. Right, okay with it? Formula works for n equals 1. Now, our inductive hypothesis. Yeah, so this inductive hypothesis. Some m greater than or equal to 1, we have x plus y m equals the sum m equals k, x to the minus k. And what is our burden? We need to show this for m plus 1. Right? If I agree with this? Okay, so I'm going to be real simple minded here. What's the easiest thing? what's the easiest thing you do? How do you get from x plus y to the m to x plus y to the m plus one? Multiply by x plus y, so let's multiply the other side by this. I'm gonna have to be careful here. Everybody, Ruby said one? So let me multiply through by x, and then multiply through by y. So this will give me two separate sums. This will give me, the first sum is going to be. When I multiply x through the sum, all it does is it kicks the x term up by one, right? So this is going to be the same business here. X. Everybody okay with it? Plus, now we're going to multiply y through, so we'll have this other side. And this time, all it does is it kicks the y term up by one. Now, any ideas on how we might move further down the road with this? These terms don't match here, right? I can't put this together because I've got mismatch on the term, right? It's kind of all killed. I'm gonna rewrite it. I'm gonna leave the first one alone. I think this is what I'm going to do. Hopefully this doesn't end in disaster. I want to re-index this, right? Um, Now, how is that going to affect the power of my x, the power of my y, and this binomial coefficient, right? So notice I need to have the same binomial coefficients. What I'm doing is I'm trying to rewrite this sum exactly again, but I want to re-index this. I want to start at one and end at n plus one instead of starting at zero and ending at everything. That's the whole thing. I'm kind of adjusting this like an accordion to make it fit, right? Well, when I change the index, that m's got to stay the same. But what changes in the bottom? Instead of k, what should I have? K plus one. K minus. Why minus one?
Because you're starting at one instead of zero.
Right. So think of it this way. This goes, as you go up, this goes n choose zero, n choose one, n choose two as you go up, right? You need to fix that. This needs to start at n choose zero. So it's actually k minus one, right? And it ends up with n choose m. So this should be, where I put an n here, you get the minus one, you get n choose m. Everybody good with that? So kind of fix that a little bit. What about the power here? I think, well, let's see. So we got to start here, start with the power x to the m, right? So we got to, whatever we do, we got to start with the power x to the m. Let's check this, right? My first power, x to the m, then x to the m minus one, x to the m minus two, and so forth, right? Is this doing what I want it to do? This will be x to the, let's say I'm subtracting k, m plus one minus one, x to the m, x to the m minus one, x to the, so that's how the adjustment should be made. Everybody agree with that? How about the power of y? That should just be y to the k, shouldn't it? Right? Because originally it goes y to the one, y to the two, y to the three, like that. And now it does what I want it to do. Everybody cool like that? All right. We're getting there, believe it or not. I'd just like to slam this together all in one big nice sum, but what's the problem now? See, I've actually fixed some things, right? What have I fixed? Notice the powers of x and the powers of y match, right? But what's the problem with the different sum limits? I've got different limits on this, right? Everybody agree with that? So, you know what? I'm gonna fix that. Okay. What one minus k one. X. One. Now notice, I'm doing a little work on these things. This thing sort of is the first sum. But what have I left off? I left off the k equals 0 term, right? This was supposed to sum from 0 to m, and now I'm only summing from 1 to m. How do I fix that? I'll put the 0 term out front. And what is the 0 term that comes out of this? M choose 0. What's the power of x? The 0 term on this one, m choose 0, the power of x is m plus 1, and the power of y is. And if you put this all back together, you get this, because now you're summing from 0 up to m. Agree? And I'm going to dissect this one the other way. Notice this one now doesn't go far enough. It starts k equals 1 for sure, but this one had the m plus 1 term, which this one doesn't. So I better stick that on there. What happens in the second sum, when k is m plus 1, what's the binomial coefficient? Right, put in m plus 1 for k, it's m choose m. And what powers do we have? That is going to be 0, and this is going to be plus 1.
X is
What's that name? Are you good yet? Yes.
sorry, how did you get y to like that one? How is it y to x instead of like
From here to here?
yes?
Well, think about the powers y and only the powers y. Originally, they start, because k starts at 0, 1, 2, 3, and now since I'm starting at 1, it's got to start at
You
here.
would start at one. Okay. Wait, I thought you were putting in m plus
What's that?
one. You're putting in m plus one.
Because that's the last term. See, here the sum only goes up to m. which I left off the n plus one term, and I had to put that back in there in white. Everybody? Okay. Okay, so what is this? N choose zero, by the way, what's in choose zero? One. So this is, you've got this row x to the n plus one. And you've got this row y to the n plus one. And then you've got this huge mess in the middle, k equals one to m. Notice the powers are the same, which is kind of the whole point. This is n choose k plus m choose k minus one x for the m plus one minus k y. Everybody okay with that? Can anybody see how we can rewrite this? Let's take this formula here. Let's replace n minus one with m. That's the same thing as n is m plus one. And let's apply it to this formula that we had in class. This is n is m plus one use k. This is m choose k. This is m choose k minus one. Familiar? So this is actually x to the m plus one plus the sum this is what comes out m plus one choose k. This is x the m plus one minus k y to the k. Okay, so which is actually sum. So the only thing really to check here is notice this sums from 0 to n plus one. So basically I've added on two terms. What have I done? I've sucked this up. Let's check this out. If I put in 0 here for k, I get n plus one choose 0, which is one, right? X to the m plus one, which is this term. And if I put in n plus one for k, this is n plus one choose n plus one, which is one. And now it's going to be y plus one. So this is just a more compact notion of this. So we're done. That's the proof of the binomial theorem, because if you notice, this is exactly the formula that you get when you replace n by n plus one. Right? So the inductive ladder is built and the binomial theorem is proved. Okay, any questions? Questions?
So if you're starting at eight plus for the middle, like that one, if you're starting at eight plus one, like, why is it not? Like, since you have the y term, like, oh wait, never mind, because there was one, it's k, never mind.
Okay, okay. Other questions? So that's the important, this identity, because it was key in turning this into the next binomial coefficient. Okay, other questions? Yes. Anybody?
Did you, from the 2019 test,
Number 3, 2019. You're talking about the exam, right?
yes.
Okay. All more questions are good too. Okay, so this is that one times 1 factorial, 2 times 2 factorial, blah, blah, blah. Is that the one? Okay, so here's the problem at hand. Show that for all n and n, one times 1 factorial plus 2 times 2 factorial plus n times n factorial equals n plus 1 factorial. 1. Okay. Okay, so what do we do here?
We use.
By the way, let me give you a little bit of advice on that exam. First of all, I'll tell you what I've told other people, so you get it all out there in the open. I don't promise I'll always tell you exactly the breakdown this way, and sometimes I won't even know, because sometimes I'm later than this in getting the exam done. But you will have 42 points coming off of the short answer of 3. What's the definition of this? What's the definition of that? So make sure you know that stuff cold, right? Be able to tell me what the common positive is, be able to tell me what, the fundamental theorem of arithmetic, or, anything like that. If the theorem, here's what I'm not going to do. What was theorem 2.3.3 from the notes? I'm not going to do that. But what I might do is I might tell you part of what's in it and say, what's the conclusion of this theorem, right? Anyway, know that stuff well. You don't have to say it exactly as it's in notes, as long as you're correct, right? So, if I ask you what's a prime, tell me what the definition of a prime is. Be careful. Don't say a prime is a number. P is prime. If it divides AB, then it has to divide A or it has to divide B. Be very precise. What was missing from my definition of prime there? It can't be plus or minus 1, right? So be careful, be complete on it. And you've got 30 points coming off of proofs or showing things like this. My advice is to do everything. Take a moment, look at the test, see if there's something that leaps out. Well, do the short answer ones for sure. See if there's something that leaps out at you that you can do. You don't have to do it in order. You just have to do it so that I can read it and figure out what you've done. Right? Try to be a little bit organized. Attempt everything. And do the problems and then go back to polish, right? Get her done, move on, make sure you cover everything, and then get back and polish up if applicable. This one, what do you think we're going to do to prove this? Induction, I mean, whenever you see something like this that involves integers or whatever, now, if you can do it some other way, good for you, but I think this one is induction. And the cool thing about induction is you can tell me stuff. If you're doing induction, what's the first thing you should do? You should do a base case, at least one, right? So for this one, that's the smallest natural number. I'm going to try this one base case and hope it holds together for me. Okay, if n equals 1, n plus 1 factorial minus 1, well, what is that? That is 2 factorial minus 1 is 1, which is 1 times 1 factorial. And then I'm done. So check them and go. Everybody agree? Base case, no problem. There's some recognition for that. What should you be doing next? Yeah, tell me an inductive hypothesis. Suppose for some m greater than or equal to my biggest base case, 1 times 1 factorial 2 times 2 factorial plus m times m factorial is equal to m plus 1 factorial, take away. This is my inductive hypothesis. Okay, any ideas on how we might move forward from this inductive hypothesis we have? Let me write down the inductive hypothesis. Any ideas what we might try to do here? That's a heck of a, let's do this. The next step in this is m plus 1 times m plus 1 factorial, right? And this is algebra, folks. So better add it to both sides. All right? So what I now have is 1 times 1 factorial plus 2 times 2 factorial plus m times m factorial is equal to m plus 1 factorial minus 1 plus this new mess. This looks good, but this needs some massage. Anybody see what we might do?
You can rewrite this as plus 2, plus 1 factor.
Okay, good idea.
Yes.
Well, so, run that by me again. So what do you want to do?
So you add like the 2 factorial terms together, so it's n plus 1 for n plus 2 times n.
Are you talking about making this?
Add the n plus 1 factorial to that expression, so like factor it into.
Do you mean pull out a factor of m plus 1 factorial? Is that what you mean?
Build and like, I guess like consolidate. I forgot what the term was. Instead of, I just think of consolidated with like, if you have n plus 1 times n plus 1 factorial, we have another n plus 1 factorial, so add that to that expression, so you have n plus 2 times.
Okay, that's okay. So the suggestion, as I understand it, is this. So that's just a little cosmetic rearranging, right? I didn't really do anything, so swap these out. And what can I do right now? I can factor out an n plus 1 factorial, right? Well, at least out of the first 2 terms. This leaves me with a 1. And this leaves me with an n plus 1. Great. And so go up there. What do I get? I get 1 times 1 factorial, 2 times 2 factorial, plus this thing here, which looks like m plus, this is actually m plus 2, isn't it? So what's this whole mess right here?
Is to the 2 factorial.
See my flair for the dramatic here. Instead of writing m plus 2, I did this. But this shows that, notice that now when I replace n by m plus 1, we get the same formula here, right? M plus 1 factorial. Right. So is that okay?
The last step.
Which one was that? Well, this is n plus 2 factorial, right?
I guess,
So remember, the original formula is this: to climb the ladder. To climb the ladder, you have to show that this formula works for, if it works, so we had it here. What you have to do, you have to come. You have to go through your motions and come to the conclusion. You have to show the formula works for the next step. So I don't know if this answers your question, but that's why I wrote it this way. Right.
I guess I'm supposed to make that. I don't think that's.
Are you with me? Are you with me here? Yeah. So what I did is I pulled an n plus 1 factorial out of the first two terms, which leaves me a 1 here, and it leaves me an n plus 1 here. But this thing right here is n plus 2, right? Because this is n plus 1 plus 1. So this thing right here, in front of the minus 1, is n plus 2 factorial.
So you put that n plus 1 factorial times n plus 2, and that's equal to n plus 2.
Right, right. N plus 1 factorial times n plus 2 is just the next fact. It's n plus 2, n plus 2. Everybody okay with this?
How would you put it? Like, would you just say like by induction?
Yeah, I mean, yeah, so how would I wrap this up? At this point, I'd say, so, you know, I would say something like, so we're done by induction. I'd say something like that. I mean, after you built the ladder, I mean, because this one's actually fairly obvious that you moved up the step, right? Yes, but you do bring up a good point. Lots of times people get very excited about solving these problems. They get there and, oh, I know how to do it. Make sure that you have your end game, right? Don't finish your thoughts, right? Give me a conclusion, you know, tell me you're done. I'm done by induction. You know, you did the base case. If you're clear like this, you will get full credit.
Is it needful to draw out n plus 2 expression? Like if we did, like if I were to like on the left part of the board where you had like n plus 1 factorial minus 1 plus n plus 1 times n plus 1 factorial. Would it be fine to the next line, right? That equals n plus 2 times n minus plus 1 minus factorial minus 1.
I will be super, you know, I'll be super formal and careful on homeworks. On the exams, something like I think you're describing, I will give a lot of latitude, probably full credit for it, right? Because I realize y'all are pressed for time.
Number 4 of 22, but maybe like part.
Is this the Bernoulli?
Yes.
Yeah, I don't really want to do part B without doing the other one first. So let me give you like kind of this, let's do the whole shebang here. The Bernoulli polynomials. Actually, how many of you have seen Bernoulli polynomials? Yeah, maybe a differential equations course. Yeah, you probably ran across it. So this is another good example of something that's kind of defined inductively. So we define these polynomials. Polynomials are defined for all natural numbers of 0. You define P0 one of the simplest polynomials that you can have. Okay, well, we define it this way. It's like a little kind of baby differential equation. The derivative of the nth Bernoulli polynomial is n times previous Bernoulli polynomial. And there's another condition, and I want the interval to be 0. So here's what's going on. Well, notice, of course, the 0th Bernoulli polynomial, when you integrate that from 0 to 1, it's certainly not 0, right? In fact, it's the interval is going to be 1. But you want the Bernoulli polynomials beyond this to have interval 0. So here's the way you do it. To get the next Bernoulli polynomial, right? So if you've got the Bernoulli polynomial p to the p sub n minus 1, you multiply by the next number, which is n, then you integrate it. Now, when you integrate it, what's going to happen?
One's gonna constant.
You're going to have this constant floating thing, right? We can't, your Bernoulli polynomial can't be different than mine. They've all got to be the same. So how do we figure out what the constant is? This, right? So that's basically it. So the first one, which is really a 3-pointer, says find P1 and P2. So this is just really, kind of a calculus problem, and also, working with this kind of thing. So P1 X. This is kind of good practice to see how this Bernoulli business works. Well, let's use this. I know that P1 prime of X is equal to 1 of P0 X is 1, right? So what is P1 X? X plus C. I don't know what the C is, but that interval condition is going to tell me. So this is 1/2 X squared plus CX evaluated from 0 to 1. So that's 1/2 plus C equals 0. So C is minus 1/2. And I'm going to need this for the second. Everybody okay with that? Well, let's find P2 of X. Following this formula again, this should be 2 times first Bernoulli polynomial. So this should come out to be 2x minus 1, I reckon. Times 2, yeah, 2 is minus 1. Do I agree with that? Now we're going to integrate this. So now P2x should be this parabola, and I've got to figure out what the constant is. Probably 6, something like that. So 0 is the interval from 0 to 1, x squared K X, which equals 1/3 x cubed minus 1/2 x squared plus kx. Value at 0, 1. And that comes to 1/3 minus 1/2, 6th plus k. That's actually minus a 6. Or minus 1/2, minus a 6 plus k. So I get k equals 1/6. So I'll put this over here in case we need it later. Okay, any questions? Well, now we get down to it because it says show by induction that Pnx is a polynomial of degree n and the highest degree term is x to the n. Well, fortunately, I've got more base cases than I can shake a stick at, right? Because I'll put the remove properties over here. So what we need to do now is we're going to show by induction that Pn is a polynomial of degree n, and the highest degree term is x to the n. Because of our previous work, by the way, what's the smallest integer for which this problem is appropriate here? It's the smallest integer. We can talk about Bernoulli polynomials. N equals 1, 0. All right, this is where we start. We start indexing using 0. True for all. This statement is true for, so I got 3 base cases for proof. So I'm not saying I need them, but I just wrote them down because they're there. I've noticed this is degree 0, and its highest degree term is x to the 0, which is 1. This is degree 1, its highest degree term is x to the 1. This is degree 2, its highest degree term is x squared, right? So in other words, there's no coefficients in front of these other than 1. Okay. So let's suppose n greater than or equal to, since after all, I bothered to do these base cases, that Pnx has degree n and its leading term, highest degree term, in this case. Now, consider the next derivative problem. where do we go from here? By the way, what might bother you at this point? How do we move forward here?
Polynomial of n plus one. So,
Right, so what we need to do is we need to find Pn plus one. Actually, this isn't even a matter. I'll write this down. But, to use that, our dollars.
Shouldn't be the n plus one times, p and x. On the left.
Yes, thank you, yeah, thank you. His correction is that should have been an image. Yeah. Everybody okay? Well. I guess to really do this, what does the PNX imply?
A and x.
Right, but by induction, I can do better. I don't know what these coefficients are. I don't know. But I've got everything that I need. What do I know about this? My inductive hypothesis is this guy has degree n. Ding, 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 degree n, right? It's a polynomial, so I only see integer powers of x, positive, well, not negative powers of x. And what other thing do I know from the inductive hypothesis? The coefficient of the leading term is 1, right? Well, let's multiply that by n plus 1. This is n plus 1 x n plus bn minus 1 x n minus 1 plus b1 x plus b0. Yes, I know this should be a n minus 1 times n plus 1, and the next one should be a n minus 2 times this one. But I am a lazy man, so I just replace these with b's. Still works, doesn't it? Because I don't give a crap about these guys out here. I'm only going to care about the lead. Okay, so far. And what is this? Well, this is p n plus 1 prime x. So let's integrate this. You all know how to integrate. What's the antiderivative of n plus 1 times x to the n?
N plus one over n. So that's
That's right. So this is x to the n plus 1. Right? And I am going to further brag upon my own personal sloth by saying Cn minus 1 xn plus Cn minus 2 xn minus 1 plus C1 x squared plus C0 x plus constant. Right? I don't want to put fractions here. I don't care. Right? All that matters is this. Everybody agree with that? And we're done. Right? That's it. Because this is a polynomial of degree n plus 1, check window, leading term, x n plus 1. So we built the line. This condition wasn't really necessary at all to show us what we do.
Is there a reason to go integrating versus going the other way and choosing the other side and using the derivative, or is either one perfectly valid?
Because to do the derivative, you've got to come down from above, right? And integrating, you're building up from above.
Right, but if you're assuming that the top line on the left hand board, if that's your form for p to the n of x,
then you can put in n plus one everywhere you have n to have the general norm of p to the n plus one. And then
Yes, but
divide
that's,
to show
you
that.
need to verify that that works in the first place, right? So if I understand you right, you're advocating replacing this n with n plus one, right? So you replace this with n plus one, and then what, you take a derivative?
Right.
Well, here's the problem. So this is another one of those kind of things where you might get into trouble. You're making the assumption that when you go to n plus one, that that's true. And it is in this problem. But then you take the derivative and it looks like what it's supposed to. But again, if that first step had been false, just because you get something true down there, you've got nothing, right? Because if the premise had been false, then you can come to a true conclusion from that. That was the danger of that implication error. So we really do, I think, need to integrate here. Okay. Other questions? Yeah, Alex.
You. Six. Yeah, can you do from the same one? 6.
Is this that, right. Show that AI. Suppose JS. Okay. Is a non-zero rule. Any one. To somewhere, M. I bet I can write the answer down without looking back at the past, right? So this is, where does it start? It starts A1 over A0 times A2 over A1 times A3 over A2 times. And it ends up with AM over A. Well, let's actually take a previous step. AM over AM minus 2, and it ends up with AM over AM minus 1. This should be. Show that by induction. Why does this work? Somebody tell me.
Because each term they cancel out all the way until you're left with.
My prediction is this is gonna be an easy induction, because that's exactly what happens. Look, it's a bloodbath. And all you're left with is two, right? That's kind of it, right? Let's see if we can carefully show this by induction.
So why in particular for this problem do you need induction to show that? Since you can write it out, is it necessary to use induction to prove this?
Not for me, but it is for you. 'Cause you're
Right, well, I
doing
was
it.
meaning like if the problem says induction, obviously, but if you were to get this
Oh,
problem
okay, I
without
see.
requiring
But
induction.
I will tell you,
would-
when it comes to that, I'll give you a lot of latitude. When I say show by induction, it's not because I'm trying to force you down the road, it's because I'm trying to help you. It's the way I did it, it's the way I think it's easiest. Now, I have been trumped by students before that see something really clever to do. Good for you if you can do that, right? If I ever want you, you absolutely have to do it, I'll make that clear. I just wrote that when I was typing it up because I was watching TV. Something goes on, really funny. And so I just put that in there. I don't care if you do it another way. Now, this way, I will be a little bit flaky with, right? Because this seems like it works, right? But, you know, there's a pattern there that has to be established, right? So although you certainly would have somebody that did what I just did right there on the exam would not have gotten full credit, but they wouldn't have gotten zero credit either. They would have probably, because I would have admired the fact that they're paying attention to what this is, what's actually going on. Right. So base case. By the way, what are you supposed to be doing induction on? Right, what's the thing, what's the letter that we're trying to build the ladder with?
And
M, that's right, this is, M is essentially how many terms are in that product, right? So if you look at the product, this is, well, how about them apples? There's only one term in the product. You've really done the multiply. This is just A1 over A0, which is equal to what this is. Because N equals 1, right? Everybody okay with that? Okay, good for us. We got the base case. Now suppose inductive hypothesis. Product A n to A n minus 1 is equal to A k over A. And we've got to show that this continues to work when I replace that k by k plus 1. So now let's just look at the next step here. Product how are you supposed to deal with that?
that's the same as the original one multiplied by, a to the k plus 1 over a k.
Right. This is the product of the first k of them. And then what's the last term? It's that. Do I agree with that? And to this, the inductive hypothesis applies. And in fact, what is that first term in the big parentheses? Should be AK over A0. And this other term should be AK plus 1 over AK. And notice the AK's cancel. I get A. And we're done by induction. Because the formula persists when I replace K by K plus 1. Any questions on that?
How do you know to know? Or how do you get that eight with this one over eight?
Right, because this is a product of K plus 1 things, all these fractions. This is a product of the first K of those things, plus the last one. And the last one occurs
Oh,
when
wait.
N equals K plus 1.
Thank
Other questions? Yes.
Just like the K, just like M.
Yeah, you know, I'm in a habit of like not using that letter there because some formality. I don't care.
the letter was asking about.
Oh, well, he noticed that I replaced M by K or whatever, and I'm not gonna hold you to that. Okay, others,
Is it correct that the older tests are representative of this level? Like the material, like this kind of material, not necessarily precisely what's going to be on the test, but like similar level of material.
in my judgment, I've missed that in both directions before. And let me give you a little pointer. Tests are always harder when you actually take them, right? I mean, it's one thing to like, oh, this is fun. And there's the island again. And it's another to like sit in a sweaty room and, oh my God, I'm from now. In fact, there's probably enough tests on there. One of the things that you might do is strategize, is pull one down to and look before and see if you can sit there and take it in an hour and 5 minutes or something like that. But yeah, you should give a shot to everything. Show me, if you know it's induction, tell me that, right? Remember, this class, a lot of this class is about communication. Communicate with me on your exams, let me know. No, I think that's a super smart thing to do. I wish I had cameras when I was in school. I would take a lot less notes, that's for sure.
Actually,
Yes. What's that?
I was gonna say it's actually worse than helpful because I'm like, oh, I can take a picture and then I don't go look back at the picture where it's writing it down, so
Yeah,
part of
but
the
it worked for
process.
me because I took the notes and then I didn't go look back at the notes, so,
Yeah.
I could work and then not look back, so, Yes.
For the cancellation properties.
Oh, right. The cancellation properties are just additive and multiplicative cancellation, so, so let him in A be natural numbers if cancel off. Right, and it's worth recording, so this might sound a little bit in the weeds, but how do you get to this conclusion if you're in a high school algebra class, you just add negative K to both sides of this equation to get this? Tell me why you can't do that in the natural numbers.
Negative K doesn't exist.
There is no negative K, so that's why this is interesting. So you can cancel them off even though there's no negative K. At this point, we haven't built the negative numbers yet, if you're like, wait. And how would you get from here to here in an algebra class? You multiply by 1/K, and unless K is 1 in the first place, there's certainly a reciprocal of the natural numbers.
You could prove them, the other way, but do that because you can show that that if m equals n, or some m equals n, by adding k to both.
Oh, right. So you can bootstrap the other way, right? So if n equals n, you can just add the same thing to both sides, yeah. Yes,
So one of these things has to define longer.
oh, I'll tell you what that is. I did mention it in class, but I understand why you didn't get it, because it's kind of, we're going to look at several well-ordering principles later, and so I'll make this, how old was that exam you looked at?
This is,
Was it 2019?
No.
It was more, so it may be that I might have gone in slightly different order. That's probably, I'll tell you what it is, and we're gonna see some other well-ordering principles. So This is what we know so far. And I bet you can finish this. Every non-empty subset of natural numbers. That's a small cell. This is called a well-ordered property of natural numbers. Yes.
What is that? Like, does it just mean like, no matter the order, there will be a small? Is that what it means? Or what is that?
No, the ordering they're talking about is the ordinary ordering that you're used to. One is smaller than two,
Oh,
which is smaller than three, and so forth. And so what that says is if you take any subset of the natural numbers, as long as it's got something in it, you can find something in there that's the smallest.
Oh.
Right. What is this equivalent to, by the way? It is equivalent to the principal mathematical reduction. That's correct. Which is kind of. What's that now? What's the principle? The principle of complete induction is the one with the subsets, right? So that's the one where, if you have a set of property that 1, 2, 3, 4, all the way up to n minus 1 is a subset of S, implies that n is an S, then it's the whole thing. And this is the one where I use previous steps on the ladder, like, so I actually introduced this after I sort of used it, really sloppy me. But, like in the problem with the stamps, the problem we did on the homework on the McNuggets, these are all, ones where you use previous steps on the ladder, not just the last step, but some of the previous, potentially. Yes.
Paradox, like, in the notes, it's like, the only thing it's like, or the only time it's referenced is like in the very first example, where it's like a paradox as it is neither true nor false, like, would we just write, like, if we had to write it down?
If I asked you what's a paradox and you said it is it's a statement that's neither true nor false, I would be very happy with that.
And then I also have a question on, like, just the properties of natural, or like properties of induction, like since induction is based on the properties of natural numbers.
Yeah, that's right. That's essentially,
Like, how come like we can do like n is an integer, like if it's like, how come n like doesn't just have to be a natural number? Like, you know.
well, as long induction will work.
If it's an integer, wouldn't you have to prove the negative direction as well as the positive
Yeah,
direction?
do it that way. I'll give you a good example of this in a moment, but, so as long as there is a smallest integer case, right? As long as you don't go infinitely far in both directions, you can still use induction. Your induction may start at -5, right? But in principle, if you look at all integers, -5 and bigger, there's really almost no difference between that and the natural numbers, or the natural numbers union 0 or something like that. Now, let me give you an example here. Let's see. So, how about this? Some may think that this could be dangerous. Um, Let me see if I can pull it. Proof raw integers again. This is. Most of it is actually my proof of those, not. Okay, so, how am I to go about this? Because I'm actually doing this for every integer.
If you do two reductions there, it's from 0 upward. I mean, but it's 1 upwards and -1 downwards.
Yeah, do that. So let's do this. Put this first for all n greater than or equal to 0. This allows induction, right? Because now I've got a base case. What should my base case be? N equals 0, right? 0 divisible by 5. Thank you. Assume now, so inductive hypothesis. That in some m greater than or equal to 0, now do it for n plus 1. Let's see what we can get. So let's build a ladder. This is going to sting. Just like this. Well, actually, I'm going to use the inductive hypothesis. Take a look at that. Okay, so let me move some stuff. Got a new 5. And I've got 5m squared. And I've got a minus 6m. And now I'm gonna put the rest of the stuff here. I've got 5m4. And, it's 10m squared. So that's taking care of these big ones. No, 5m, yeah. Got 5m. Oh, yeah. 5m plus 10m is 15m. And then I get a minus 5. Doesn't get, I think I do. No, I don't. I get a 0. Let's see. And what do we know? Why do I have that first group by itself? Parentheses.
Because by the inductive hypothesis.
We know that this bit is 5k. It's 5%. Would everybody agree there's a factor of 5 in this? So this is divisible by 5. So statement. If I can remember what it is, M5 is 5m squared, 6m is divisible by 5. For all n greater than 0. Okay, how do we go on from there? We could, I think you suggested doing induction in the other direction, we could do. Let's do this. Now spoken is negative. So. Negative n is greater than 0. So. Previous. Negative n. There. Plus 5 times negative n squared minus 6 times negative n is divisible by 5. Do I agree with it? So. Uh, am I okay with that? Yes.
For this particular one, wouldn't it be faster just to show that, for for mod n equals 0, 1, 2, 3, and 4, that it's true for all those cases, and then it's.
That's right, but we haven't done that yet.
Okay.
Yeah. Everybody agree this is divisible by 5? So is this. Oops. Because all I did is I changed the sign, right? So. Uh, so- Right. So. Because that's divisible by five.
You intend to change the.
Yes, the exponent is five first term.
What did I do?
Here you have n to the five, there you have n squared to start off.
Yeah, right, completely. Freaked out, that's a five, that's a five. There we go, thank you. Does everybody believe me now? Because that was just a five, and that is, now put these together. I will jump for unless. Didn't use induction, just kind of bootstrap it. We had. Okay. Other questions? Yes.
What did we find here move to like say somehow maybe more like it's the five n squared is always like five, therefore if n to the five minus five squared minus plus five squared minus six like five n to the five minus six plus like five, we'll just work on that instead.
Correct me if I'm wrong, I'm gonna maybe paraphrase what you're saying. You said, hey, Jim, why don't you just take five square out of this, this is five.
Yeah.
And then, yes, that would work. If you made that observation at the beginning and said, look, this is gonna be a five, all I have to do is do that, I would consider that very clever shortcut. Oh, you're welcome. Yes.
Can you explain why, like, you were able to just throw the n plus one n, like, out, like, from the, before you erased on that side, you just put n plus one, when you were doing the induction, I thought that would be like, assuming the conclusion you're working from.
No. Here's what we have. So we'll take you back to what we had before. We've had. This is what we have. This is our ladder. We're assuming that we have, what we're trying to do is show if we've got the n one on the ladder, we've got the n plus one. Now. When I did this, maybe this is your concern.
Yeah, that's one kind of confused.
This is the next step on the ladder. I have not concluded it is divisible by five yet. That's what we have to do, right? This is the next step, kicking it up, kick m to m plus, and I did this up here too, I'm sorry about that. Kicking m to m plus one here is the next step. What I haven't done yet is conclude it's divisible by five, and that was all that business here, when I multiplied it out. This is, you see how fast I can do it. Five m4 plus 10 m3 plus m squared plus 10 m plus 5m plus 1 plus 5 m squared plus 10 m plus 5 minus 6 m minus 6. Right? That's what I got there. And I still don't know this is divisible by five, but that's when I did this grouping here.
And then you can pull five.
And
Yeah.
this is where I applied the inductive hypothesis. This chunk here is divisible by five, and the rest of this mess all has a factor of five in it. Does that clear it up?
That makes sense.
Six.
From which one?
From
2018.
2018.
What do you think this? How many numbers between 1 and 10 to the 6th inclusive are neither a cube nor a square? We can probably bootstrap this one. Um, So.
Yes.
That's 1 in a million. How many numbers between 1 and a million are neither a cube nor a square?
And we use set of squares that are less than a set of cubes that are less than six. Let's subtract the back that like back numbers all ones of those sets set and add back for elements. That's
How many total numbers are? A million, right? By rate, 1, 2, is another million, right? How many cubes? Well, how many squares?
well,
2,000.
it's 1,000 squared is 10 to the 6. So all of them are less.
Here's what they look like. 1, 2 square, 3 square. All the way up to 1,000. 1,000 of these. Right? How many cubes? Two, 3 cubes. That's 100. Good. So. What are we doing? I mean, there should be a lot. Most numbers should be either a cube or a square, right? I mean, they're cubes and squares are pretty spread out. So how are we gonna go about this?
Number. First, you have to find the number of elements in each intersection. Because they're intersections 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 6.
Okay, so. And throw out. Every. That is either. A cube. Or a square. Everybody agreed that this is how we'll get all the numbers between 1 and a million that are neither a cube nor a square. Take all the squares and all the cubes, toss them. So to count this, I'm gonna, so let S equal to squares. Let C equal to cubes. Right, so in fact, this is the set of squares, and this is the set of cubes, right? I need to find out how many elements are there in the union. And that this problem doesn't solve. See. What? Fine. Yes, that's. So what does it mean to be both a square and a cube? Here they are, 1, 2 to the 6, 3 to the 6, all the way up to what? 10 to the 6. There should be 10 to 6 powers. Right. Everybody agree with me? So how many squares were there? 1,000. How many cubes were there? 100. And then you had to throw out the 10 that were overlap. Everybody okay with that? So that's like 1,100 minus 10, which is 1090, something like that. Can I have right? So I guess we said, how many are neither squares nor cubes? That's how many numbers there are between 1 and 1 million. And it looks to me like the number of things, the union of the squares and the cubes comes to 10 million. So this is like 9, 8, something like 998,910.
So why would I just like subtract, like, why would we have to subtract the six, or no? the-
Right, because, for example, look at the number 64. That is a square, so it's here, and it's a cube. Oops, I counted twice. That's why I tossed it.
How did you, I might just be dumb, but how did you figure out that a square and a cube is to the 6th power? Or did you just intuitively know that?
Well, actually, it follows from unique factorization into primes. But if you have, let's see if I can get this way. I will not give the prime factorization here. But see if I can get short of it. So suppose, let's do it this way. Suppose that x is a square.
Thank you.
Right, x is this way. So it's a square, it's a square, so it's a cube. Suppose P is the prime. And P times S. And I don't know, when I gave the test, I may have given them that, I don't remember. But I'll give you something concrete. Suppose P divides Well, if P divides X, then P divides B squared, right?
Yeah.
This means that, P divides B, because P is prime. Because it divides B times B, so that's. So that means that X, so that means that B is B prime P. So X is B squared, which is B prime squared, B squared. Well, this also means that, P divides A cubed, which implies P divides A, again with prime. So A equals A prime P. So A cubed, which is again X, is A cubed cubed. Right? Let's see, now I'm gonna have to bootstrap this. Now, notice that you can cancel two powers of this. Cancel two powers of B. Right? Now you have P divides B prime squared. Right, so now you've got four powers up here. Right? Now you cancel again and you get P divides A prime cubed. So you now get three more powers here. And it evens out at three because both two and three divide six. Okay. So the conclusion we come to is every prime factor that divides X has to divide it 6 times. All right. So. Yeah, I probably did that one. So, yeah, so, something like the intersection of squares and cubes is how or something like that. I wouldn't want you to get stuck on something like that. I'll see if I can give you, a short first, but essentially you can go through it, show that every prime that divides X has to divide it 6 times. I mean, you go by induction and show it 6 times.
Well, is it really correct to guess that, like, oh, if it's a I guess 6 because like a square and be like 2 times 30, like if you multiply the exponent to 6, is that incorrect?
Well,
Because then it's,
so what you do need is you need unique factorization of this to be correct. You need the property. For every, for the squares, everything's a square and a cube is also a 6 pound. You're welcome. I've got one that's probably sure. So this is, so X is a square. So X. Or PIs are prime. And the AIs are greater than. This is the prime power factorization. I'm putting this down here. Now, since X is a square, this means it's a square of something. Now, that means that whatever squares to it has these prime factors, right? And that means that A1 is divisible by 2. Everybody agree with that? In fact, not just A1, all the AIs are divisible by 2, right? Because the fact it's a square, you need factor. This is the best way to do it. since X is a cube, that means that each of these are divisible by 3. So what does that mean? That means 2 and 3 are relatively prime. And if 2 divides this, 3 divides this, it's a relatively prime, 6 divides this. So 6 divides AI. Right? Which means that each one of these is divisible by 6, so it's a 6 prime. That's another way to do it. Okay, other questions?
A question about 2.4.3, but it's
Thank you.
actually not 2.4, or, well, it's 2.4.3, but like multiple sets. So like, I know like the union, you would subtract the intersection of the two sets, like if it's 2 sets, and then the intersection, you would subtract the union of the 2 sets. And then, so if it's multiple sets, you add the intersection of all 3 sets, or however.
All
many
right.
sets there. And then if it's the intersection of all the sets, would you just subtract the union of all the sets?
You know,
Like
you can figure it out yourself, in the following way, one of many ways, because we know this is kind of a baseline thing. Right, so that's kind of the first thing that we talked about. And this is where, okay, count everything in the union of, A and B, count everything in A, count everything in B, and toss everything that you double count, right? Yeah.
that equal the A to A.
Yeah, that's a good idea, I think. So sometimes people get, oh, it's a little bit of a mystery where that other one comes from. Well, check this out. This is another kind of inductive. Okay. Replace B by B union C. So this is. It's just the same formula, just applied to the set B union C. So let's see what comes out of this. This piece right here is because it's just the same formula up here, but instead of A up at C, right? So let's see what we've got so far. What's this? And then we've got this pesky. A intersect B union A intersect C. Okay, so this is a union too, right? So let me take a little aside here. This will do a little computing over here. A intersect B union
A.
A intersect C. Apply the formula again. This is A intersect B plus A intersect C. So far, so good. Minus the intersection of these two, which is A intersect B intersect C. Now let's throw this back in here. Whatever I got over there, I'm subtracting it now, so let's be careful. That's minus A intersect B minus A intersect C minus minus, there's the plus. interstate B. So really, this formula is no different from the first one. It's more long and convoluted, but you just put in a B, U, and C where we saw B. And well, now you can go further. Because now we've got this. All right, this is my starting point. Now replace this by C, U, D, looky here, and go through this, and you'll get the one for 4. And you see it kind of gets out of hand, but this is called inclusion exclusion, right? Inclusion, ooh, exclusion, inclusion, right? That's what you do. You add it up, throw it out, correct it. And it's with a lot of sets, you can see there's a lot of back and forth. Does that make sense?
Yes.
Okay, other questions? Anything else?
One last thing for me, I got stuck. The work on the homework, we had 2 summations. And where I got to, I can show you. You said carry it out a little bit, and I noticed there's obviously a pattern and something cancels out. But I don't know. Kind of how to go there.
Or you just gotta combine a couple fractions on one side of the equation. Remember the way. So, tell me what the problem is.
You have this right here. So